So the last time we talked all about value iteration. Which was an incremental procedure to calculate better and better approximations to the optimal value function. So in an MDP, as usual, we have the Bellman operator of the MDP. The optimal value function is the fixed point. And if we had a policy pi, which is greedy with respect to the optimal value function, then we know that pi would be optimal, which just means that its value function is v star. So value iteration was this procedure that you start at some initial function that assigns reals to states, and then you iterate this with this Bellman operator, Bellman optimality operator. So I call this the Bellman optimality operator. This has the max in it, as opposed to this T pi, that's the Bellman operator for policy evaluation, for evaluating policy pi. Or in short, that's just a Bellman operator for pi. So we iterate the Bellman optimality operator, and we know that this iteration, because of the contraction mapping theorem, converges to v star in max norm at the geometric rate and the last time we calculated that if h is 1/1 minus gamma, the effective horizon in this discounted MDP, then after, if n is greater than or equal to 2h times log, and here I forget something, h cubed, I think, or h squared, question mark, you look it up, divided by epsilon for some fixed epsilon, then if you take pi to be a policy which is greedy with respect to Vn, then pi is epsilon optimal. Which means that V pi is epsilon close in maximum norm to V star. So using pi is not going to lose more than epsilon, no matter what the initial state is. This is the number of iterations that we need to run this procedure for. It's basically proportional to the effective horizon and proportional to the logarithm of the reciproc of the precision. The total effort that is required by this procedure to calculate such an epsilon optimal hypothesis is going to be the iteration number times how much it costs to perform one iteration here. So to see how much does that cost, let's write in details how this calculation looks like. So the operator, if I expand this definition, is doing these things. It's taking the max over reward plus future expected value and the current estimate of the optimal values discounted by a factor of gamma and take over a max. So going from inside to first, okay, so going from here, to calculate this function, we need to calculate a value for every s. Okay? So that's going to be s times the calculation that you need to calculate the value for a single s. So this equation right now is written for a single s, but you have to do this for every s. So that's s times something. And given your s, then you can take an arbitrary action A. And for each of those actions, you calculate this value here. Okay? So there are A actions. So it's going to be A times the cost of doing this calculation. But maybe this is not a good way of doing things. But okay, so keep in mind this s times, and let's just go from inside. So you have a fixed s and a fixed a. You just need to do this calculation. Which part of this calculation is costly, and how costly is this? Okay. Yes? So the probability times the value, and you need to sum, right? So that's the expensive part, because you need to, well, okay, maybe multiplication is a little bit more expensive than addition, but in addition to that, you have to do this s times. And we are sensitive to, if s is big or a is big, this is going to take a lot of time. Okay? So this, for every fixed value of SA, this costs you S elementary operations, S multiplications, and S additions. Once you're done with that, you can multiply the result with the gamma. That's one more. Okay, we ignore that's S plus 1. And then you have to add the reward. That's S plus 2. So it's basically order of S. So in the order of S. So this costs you, this whole thing for a fixed S and A costs you S operations. And now you have to do this for every action. So that's A times as much. And after you calculated this for a fixed state and every action, you have to take the maximum value. You can do that incrementally. You're calculating, you know, one of these values. Is it bigger than the previous largest value, and so on and so forth? Storage-wise, that's good. Altogether, this is going to cost you, together with the max, so maybe going here, this is going to cost you S times A. So altogether, because you have to do this for every S, the whole cost of a single operation is going to be big O S squared A. Okay. So the total cost for value iteration is going to be 2h log something 2a squared over epsilon times S squared A. In the order of this. Okay. So I can get rid of the 2 because those can be in the ordo notation. Okay. So we see that the amount of calculation we need depends on the number of states we're going to have, the number of actions in a very clear fashion, quadratic dependence on the number of states, linear dependence on the number of actions. In addition, we see a linear dependence on age. And we see a logarithmic dependence on the reciprocal of the precision, which is kind of like you're increasing the precision, then it's not going to impact much how much effort you need to put into calculating such a good policy. All right. Any questions for this? Just recapping and summarizing of what we had before. Yeah. This one? Right. So V pi tells us how good our policies are. Okay. And V star is how good they could be. So V pi is below V star. So if you want to plot it, for example, this is how it would look like. Here are the states. Somehow, maybe V star kind of looks like this. Who knows how it looks like? And V pi for any policy pi is going to be some function. Maybe it goes negative, by the way. Like, it doesn't matter. Like, maybe even V star goes negative. Who knows? So these are larger values. Larger values are better. And V pi is going to be below V star. And for any state, if you take a state here, and if you look at the difference between the value that V star takes and V pi takes, then this difference tells you how much you're losing by using policy pi instead of an optimal policy. So if you see big differences, that's a problem because you're losing a lot. The expression we have there is just V star minus V pi. Well, I wrote it V pi minus V star, but it doesn't matter because we take absolute value. Anyways, V star is always bigger than V pi. You can always just think about V star minus V pi. That's non-negative, and you take the maximum value of that. So the maximum loss that you're going to suffer if you're using policy pi instead of using an optimal policy. And so we want that to be smaller than epsilon. Okay. So it's kind of a robustness result because no matter what the initial state is going to be, if you guarantee that this difference in max norm is less than or equal to epsilon, that means that the policy will never lose more than epsilon in terms of the expected return than using an optimal policy. And so in practice, you would set this epsilon to be small enough compared to what your expectations are of how much value you should be getting, such that you don't care about those small errors. Sometimes it might be difficult to set this epsilon if you don't know the magnitude of V star. So here, we are not really thinking about this, but if you're thinking about a specific problem, then there is the question of, okay, like I want to use this procedure. How do I set the epsilon? Well, if V star has this big range, then maybe compared to the range of V star, like some epsilon, you can say, oh, 10% of the maximum return would be nice to lose at maximum. But if you have no idea about what the maximum return is, then how do you know how much 10% is? So it's like, it's not completely obvious that setting an epsilon and saying that, okay, you're only losing epsilon is a good thing. If every value is small compared to your epsilon anyways, like even the optimal value is small, then maybe you want relative precision or something like that, and you're not getting that here. You could try to modify the procedure for that setting. But yeah, it's for a lot of problems, you get the sense of like, maybe just have some policy, you run it, you see that, oh, it's already getting this much value. And then based on that, you're setting your expectation of like what epsilon should be. All right. All right, so that kind of finishes our discussion of value iteration. I hope that the algorithm is clear. Let's move on to policy iteration. So we had this picture before that we had the space of functions that map states to rewards. And then we had the space of deterministic policies. And you start at V0, and you take steps with policy, with value iteration. So you get the Vn, you apply T, you get Vn plus 1, and somehow you're hoping that it's getting close to V star. And at one point when you're deciding that, okay, like maybe I'm close enough, then you take the greedy policy with respect to Vn. That gives you this pi. And then you look back and you're asking, is this a good policy? Where is its value function? Is it close to V star? So that's policy evaluation. Going back. So here you're calculating a sequence of functions over states, real valued functions. And then one point you decide to stop. You read out the policy. You return that policy. And we argued that this policy is going to be a good one after that many iterations. Oh, by the way, here, this also assumed here that V0 is equal to 0. As for simplicity. Okay. And then last time we had this discussion that, okay, maybe this is not the only thing that you can do. You could do instead of doing this calculating just with the BAM on optimality operator, a sequence of functions here. You could go back and forth following these two arrows. And that is also an algorithm that has a name. It's called policy iteration. So kind of the same picture, but it's a little bit more crazy. So you start with a policy, actually. You start with P0. P0. And then you evaluate it. You get some value function for this policy. And then you look at it and you say, oh, okay, like maybe not this value function. Let's take, not this policy, but let's take the greedy policy with respect to this. So there's a policy evaluation step. And then there is a greedification step, taking the greedy policy with respect to this value function. So that's your pi1. And then you can evaluate that. You get V of pi1. And then you can greedify it. And I'm drawing it as if like something would be, this would be going somewhere. That just so that my drawing is not totally crazy, but you can't really expect any such orderly behavior of these procedures. That's just for the sake of keeping the drawing simple. But it turns out that this is not bad either. So this was value iteration. This is called policy iteration. They call it policy iteration because it chooses a sequence of policies, fundamentally. I mean, value iteration in a way, like for every Vn function that you encounter, you could choose the greedy policy with respect to that. I'm in trouble. Wow. No. Freed myself. Oh. Okay. So you can think about that this is also producing a sequence of policies, but it's not going back and forth and not doing that way of producing the policies. It's making steps here, and then you can read out in every step one policy. But this process is fundamentally different. It's about jumping back and forth between the two spaces. Policy space, value function space, back to policy space, back to value function space. Zigzagging. If we want to write this formally, we can write it as follows. We choose an initial policy. And in iteration, I don't know, n, the next policy, what is the next policy? The next policy is going to be greedy. I used the notation before, so let me recycle that notation. So I told you that I'm going to say that if pi satisfies something like this, then pi is greedy with respect to v star. So gamma is this operator that gives you all the policies which are greedy with respect to some value function. So greedy policies are not unique. So gamma gives you this set. So this is gamma of v of n here. And this pi was just one element. And here as well, when I'm going back here, then there is a whole blob of possible choices of greedy policies. I just pick one. Again, there is a whole blob. So pi of n plus 1 can be a greedy policy with respect to the value function of pi n. So now I'm just focusing on what does a policy satisfy here? The next policy, pi 2, is greedy with respect to the previous policies, pi 1's value function. This is the greedy operation. Take the policy that's greedy. One line. That is some subtlety here. If you want this procedure to kind of be sensible, then when you have multiple choices, because you have ties when you're choosing the greedy actions, then you should be choosing in a consistent fashion. So let's say you're ordering the actions, and you call them from 1 to a. And you always, if there are pi's, then you always prefer the action with the smaller index. That would be a consistent way of choosing the greedy actions. If you do this, then the benefit of that is going to be that if you have ties, you could be switching between policies for no good reason. Then you could have stopped because you're just going back and forth between two actions. Both of them look equally good, but you never realize that, well, I actually could stop because both actions are equally good. So I could just like stick to one of them. So break ties consistently here. In practice, this is not a big issue. Like this ties pretty much will only come up if you're constructing an example on purpose, such that they should come up, or you have some strange, maybe you can get into trouble if you have a discrete Metish-like problem, like us in a graph or something like that, without discounting. So all integers or binaries, and like then there could be many ties. And if you are not too careful about these ties, then the algorithm may not stop when it could have stopped. But if you have a lot of real numbers around, gamma, probabilities, whatnot, then it's not very likely that ties are ever going to come up. So it's like we had this exercise at the very beginning about the bandits. I think the very first exercise. And it was like, oh, if you ever see ties, then you choose uniformly at random from the actions. Totally doesn't matter. You will not see ties, most likely. It only matters if you are developing algorithms for some discrete math-ish kind of things. Anyways, all right. So this is the algorithm. It's very compact, and if you expand it, it has a lot more steps, right? So if you have pi n, so this is for n greater than or equal to 0, then you have to first evaluate pi. So that's policy evaluation. So how do we get v pi n? That will be step number 1 if you're expanding like what you need to do when you implement this algorithm. Then you need to calculate for a policy pi n its value function. And step number 2 is going to be calculating pi n plus 1, which is going to be this greedy policy with respect to the value function of pi n. We'll talk later about the cost of doing each of these operations. Let's first see what we can say about this procedure. Any questions for the algorithm for policy iteration? It's clear what it's doing. It's jumping between these two spaces. Okay. All right. So the claim we are going to make about policy iteration is that it's never slower than value iteration in terms of iterations. It's kind of at least is going as fast as value iteration. In particular, the following is going to hold. So this is going to be a claim. So if I define v naught to be the value function of the first policy, phi naught, and then I define vn plus 1 to be Bellman operator applied to vn. Okay, so that's value iteration. Then the following is going to hold. V star is sandwiching v pi n. So v star is an upper bound on v pi n, and vn is a lower bound on v pi n. We already know that vn is converging geometrically fast to v star. And so once we establish this sandwiching, so this is kind of like the stuff between the two breads, then it will follow that v pi n also has to converge to v star geometrically fast, right? So that's immediate from this. because you can write that v star minus v pi n. So from this, it follows. That's not part of the statement. It's immediately following from it. That it's larger than or equal to v star minus vn. And we know that that's geometrically fast, converging to v star. Okay, so this is just an immediate corollary. And so then that means that this procedure is at least as good, if not better, than value iteration. In a way, it's kind of feels better because you don't have to do an extra gridification step in a way. Like when we were going from Vn to the policy space and we were coming back, we were losing a factor of age in terms of the error. So this is not doing that because it's already arguing for the value function of the policy that was produced. So that feels like some advantage. Doesn't feel like a big advantage, but maybe some advantage. All right. Is this clear? Okay. How do we prove this? So we want to prove that that relationship holds. We're going to do it by induction. It's an iterative algorithm. It kind of makes sense to try to prove this by induction. How does induction work? First, we have to establish the. How do you start induction? Base case, yeah, that's right. It's been like a long time. So what's the base case? Base case is when n is 0. Yeah. When n is 0, how does our inequality look like? We want to show that v star is at least as large as v pi naught, which is at least as large as v naught. Does this hold? Okay. Why? We just, can you say it louder? They are equal, yeah. We defined v naught to be v pi 0. It was a clever choice, so that this holds. And of course, this inequality holds because, and we will not need to discuss this anymore, because v star is an upper bound for the value function of any policy. Okay, so that was easy. So assume now that v star, we have already shown for some n this. Let's say up to n greater than or equal to 0. We want to show it for n plus 1. So this is going to hold for n plus 1. So the only thing that we have to worry about is whether v pi of n plus 1 is at least as large as vn plus 1. Vn plus 1 is t applied to vn plus 1, was t applied to vn. So we need to show that v pi of n plus 1 is at least as large as t applied to vn. What do we know? So let's write down the goal. The goal is to show that v pi of n plus 1 is at least as large as t of vn, which is equal to vn plus 1. What do we know about pi n plus 1? Everything else is known here. So pi n plus 1 is kind of the new quantity that comes in. What do we know about pi n plus 1? How was it chosen? It's the greedy policy. Greedy with respect to what? Value function of what? Pi n. That's right. So pi n plus 1 is greedy with respect to value function of pi n. Formally, how do we write this? T, what? Okay. Is equal to well, I just want to write these T's because otherwise it's going to be a lot of writing. I think maybe this. Let's use that. Right? So T of v pi n is T of pi n plus 1 applied to v pi n. This is what we know. What else do we know? We also have an induction hypothesis. And the induction hypothesis says that v pi n is at least as large as vn. Okay? So I want to bring in somehow, I want to have pi n plus 1 and somehow t applied to vn. So I'm going to use the induction hypothesis. So the induction hypothesis says that v pi n is at least as large as vn. So from this, I claim that it follows that if you apply t on both sides, you get the same inequality. So in other words, t keeps inequalities, or t is called monotone in such cases. So for this, we need to remember what the definition of t was. It's kind of here. So if I write out, I don't know, t of vn at s, this is how it looks like. I have vn there. And then the probabilities are non-negative. Gamma is non-negative. If you're taking the maximum of numbers which are larger, then you get something larger. So since v n s prime is below v pi of n s prime, I can replace this guy here by v pi n s prime. and I will get something greater than equal, right? So you can argue by going from inside to outside. So first you can say that, okay, just look at this expression. In this expression, if I replace Vn by these larger values, I get something larger. That's because these values are non-negative. I'm summing them up. Then this expression, the same holds because we are just shifting this by the same constant value. And the maximum is also monotone. If you have a bunch of numbers and you have a bunch of other numbers, and each number in the second set is at least as large as the numbers in the first set, the maximum of the second set is going to be larger than the maximum of the first set. So you're just using this. And this here, the right-hand side, is t applied to v pi n at s. And the short way of writing that without s and all these parentheses is just to say that tvn is a lower bound for t of v, t applied to v of pi n. There is no n plus 1. Okay. This is called monotonicity. If you have a function that keeps this ordering of the functions, then we say that this function is monotonous or monotonic. Okay. So we have this inequality, or this equality, and we have this. So 1 and 2 together. So this proves 2. And 1 and 2 together give you what? They give you that t of pi n plus 1, v pi n, is equal to t of v pi n, which is greater than equal to t of vn. Okay. Our next problem is that, okay, this is good. Like we have pi n plus 1, tvn, and we want to have these inequality. We have pi n plus 1, we have tvn, but this is the value function of pi n plus 1. We don't have the value function of pi n plus 1 yet. How can we get that? What do we know about the value functions of policies? That we used already quite a bit. We love these operators. So think in terms of like, okay, how do I connect the operators that are on the board to the value functions? So is there a connection between this value function and, let's say, this operator here? And if there is, what's the connection? That's correct. The value function is the fixed point of that operator. What does that mean? That means that if you apply the operator to the value function, you get back the value function. We also knew that this operator is a Gomo contraction. If you keep applying it to some value, then as you apply it more and more, the resulting functions get closer to the fixed point at the geometric rate. That was the contraction mapping theorem. And we concluded before that this was a contraction map. Okay, so can we use this somehow? If you look at this, what we got so far is that we apply the operator once to some function. So wishful thinking, how about like if we could get the same inequality, but here, instead of applying this operator once, we would be able to prove the inequality when we apply this operator twice or 3 times, and so on and so forth. Baby steps. Let's see whether you can do this when you apply this operator twice first. Okay. Applying this twice, well, it suggests that maybe we should just apply the operator on both sides of this inequality and then see what happens. I'm missing something. So again, this means that t pi n plus 1 is applied to both sides. Sorry? I'm not sure I understand what you're saying. TV pi n larger than t pi n? Sure. Okay. All right. I think that's yeah. So it's clear. I just want to explain what was happening. So the previous idea was kind of not quite good. So Shuai is helping out. Thank you. We use some other ideas. So this, like if you apply this operator t to any function, it gives you larger values than if you apply t pi for any pi to the same function. And the reason is because in the t operator, you have the max over the actions. And this other t pi operator just have some sum. And so the max is always bigger than that sum. So this inequality holds because of that. And then we know that so V pi n is the fixed point of TPn. So this inequality holds. And this was the induction hypothesis. And so now you can apply T pi n to both sides. T pi n plus 1 to both sides. So you apply T pi n plus 1 to both sides. And OK, so right. Then you get that this is this holds. And then from here, you can also conclude the same way. We already concluded, how was this? OK. I think, OK, so apply T pi on both sides. But we have to write the whole thing. So this is equal to that. Apply T pi n plus 1 to both sides. You get this inequality. Wait. Oh, yeah. You have go up to there. OK, so apply here T pi n plus 1, and apply on this side T pi n plus 1. Then we get T pi n plus 1 squared. V pi n is greater than or equal to T pi n plus 1 applied to V pi n, which is greater than or equal to T pi n plus 1 applied to Vn. Is that? OK. No. OK, this is this is T of V pi n, and T of V pi n is greater than or equal to T of Vn. OK, on one hand, and at the same time, using this logic, it's greater than or equal to Vn as well. OK, I ran out of time. You keep applying. The right-hand side is going to converge to V pi n plus 1. And if you do this carefully enough, you find, lo and behold, that V pi n plus 1 is at least as large as T Vn. I guess, OK, the notes, like if you got confused, I got confused. So I assume you also got confused. Sorry about that. Sometimes standing too close is not happening. But the notes do have the clean two-line calculation. If you know in what order you have to apply the inequalities, it's all fine. All right. So that shows that policy iteration is at least as fast as Y iteration, and that kind of closes dynamic programming. All right.